Have any of you ever sat in a math class wondering, why am I learning this? Because I definitely have. And whether you're in Algebra 1, studying all the way up to calculus, I'm sure you can all relate. And we've all heard that repetitive answer, math has applications everywhere. I mean, society could not be built without math. But often these applications are hard to find. I mean, how could something like imaginary numbers, which Newark Academy students learn in Algebra 2, how could something like that be applicable in the real world? And more importantly, why would someone even choose to discover it? For those of you who don't know, an imaginary number is simply the square root of a negative number, denoted by I. Now this concept always puzzled me. I mean, how can a number, when multiplied by itself, become negative, hence the name imaginary? I mean, I can just imagine a mathematician looking at this undefined result and saying, I'll just call that I. And everyone celebrates this amazing achievement. I mean, why can't I just look at 0 divided by 0 and say, I'll just call that A? But the real story of how imaginary numbers were invented is much more interesting. Beginning all the way back in ancient Greece, as most math stories start, we had the ancient Greeks answering the question, why do we study math, with the most obvious answer. We want to predict the motion of planets, we want to make beautiful architecture, and we want to quantify the real world. This was reflected in their process of problem solving. For example, solving the quadratic, they used a very visual and intuitive way of solving it by setting each term to the side length of a square or a rectangle and setting the area of the square equal to one of the variables. And this method is called completing the square. However, when solving a quadratic, we can yield negative results. And when the Greeks saw this, they had no intuition for it. I mean, how can you have a side length which is negative? It's impossible. So the Greeks decided to limit themselves from all negative numbers completely, limiting any growth in mathematics. Then, when solving the cube, even though it looks much more complicated, it's essentially the same thing in 3 dimensions. And this is how Italian mathematicians chose to solve cubic equations. Now, even though the equations look much more complicated, they all have the same premise of plugging in numbers and you get a value for x. However, at this time, the Italian mathematicians had already accepted negative numbers as something intuitive. However, when plugging into this equation for a regular cubic equation like x cubed equals 15x plus 4, you can get a negative number under a square root, which is an imaginary number. Now, there was definitely no intuition for this. These Italian mathematicians decided to limit themselves from imaginary numbers, just as the Greeks had with negative numbers. However, when choosing to use a growth mindset when approaching this problem, you can actually yield a normal and intuitive result like x equals 4, if you just choose to denote an imaginary number with I. And even though there were absolutely no applications in mind when choosing to denote an imaginary number with I, eventually, 3 to 4 centuries later, we have applications such as in Schrodinger's equation, which models quantum particles, or even in electrical circuits. Now, why am I telling you this story? I mean, it might just sound like another useless thing you learn in a math class. But this marks the transition from applied math, just as the Greeks had done, to pure math, which is where you study math just for the sake of it. So with this transition, David Hilbert decided to ask the same question you've all been wondering. Why are we studying math? And he decided to answer his own question with the concept of a complete formal system. A complete formal system is this ideal yet unrealistic goal for the end of mathematics. A formal system is simply one where we start with a couple basic assumptions called axioms, and we build every theorem off of it. And a complete system is where every theorem has a proof. Now, just some examples of these axioms. First, we have Euclid's 5 axioms, which we've all learned in geometry, as well as axioms for arithmetic, which may look much more complicated, but they're really very basic. For example, the first one translating to there are no negative numbers, which is a very limited approach, just as the Greeks had taken. So this concept of completeness is essentially David Hilbert's idea of why we study math. However, in 1931, Kurt Gödel, who encountered this concept of completeness, decided to disprove each and every aspect of David Hilbert's concept of a complete formal system. He started with this logical paradox, which many of you may have seen. This statement is not true. Of course, this is a paradox because if it is true, then it's false, and if it's false, then it must be true. Thus, there's always a contradiction. Now, how does this apply to math? Kurt Gödel showed that this statement is not provable, which is essentially the same thing, must show up in math through encoding a statement to a number with a process called Gödel encoding, then showing that this statement must show up through the infinite functions in math. But that might not make any sense to you, so an analogy, which made a lot more sense to me, that explains this concept of self-reference, where a statement refers to itself, and that's where these contradictions appear, can be seen from the show The Office, with most people's favorite character, Dwight. So the reason that statement made essentially no sense was because he started off with Jim is his own worst enemy, another self-referential statement. And this is where the contradictions appear in his dialogue as well as in mathematics. So we come back to the central question of why do we study math? If it isn't to have a visual understanding, just as the Greeks didn't have a visual understanding of negative numbers, if it isn't to have any intuitive understanding, for example, with imaginary numbers, or even to be looking for applications, such as the discovery of imaginary numbers, then why are we studying math? Well, all of these discoveries came about through mathematicians' genuine curiosity. For example, why would a jazz musician play music? It's because they genuinely enjoy playing music. Or why would a writer choose to write books? It's because they have a genuine curiosity and enjoyment in writing books. This same idea can be applied to mathematics. And having a genuine curiosity in seemingly inapplicable or non-intuitive problems, we can eventually find applications that can benefit the world. Thank you.